Our second paper will be the thermal and electrical property of nano-silicon dioxide field epoxy system for use in high voltage insulation by Martin Already. Martin achieved a physics bachelor degree from the University of Reading in the UK before moving to the University of Southampton and complete a PhD based on the electrical characterization of polymetric material in the Tony Davis High Voltage Laboratory. Martin has since graduated and is continuing his work into polymer composite system and the High Voltage Laboratory as a member of research staff.
Okay, thank you very much, Mr. Chairman, and good morning, everybody. Okay, so very much following on from the first talk we've had this morning, I'm just going to talk to you about some work we've been doing with epoxy filled systems. We've used some micro and nano. Obviously, since everyone's tending towards nano these days, we'll focus a lot more on those. Okay, so first off, obviously, over the last couple of days, you will have heard a lot about polyethylene XLPE, which is there's a lot of the way forwards here there for cables, but also for other areas such as joints or bushings, then epoxy is also a good option. So just covering some real basics, just in case anyone's been hiding away and hasn't heard about epoxy. The idea is that it's a thermosetting polymer. You mix two stable liquids together, which chemically cure or harden, cross-link together, forming a rigid, tough structure. These often have advanced mechanical properties, such as rigidity and toughness, which unfortunately is one of the reasons that they're often not considered for cables, because they're not flexible enough. But they also have fantastic electrical properties, highly insulating, as well as good thermal and chemical resistance. Okay, so in particular for high voltage, some of the main reasons that epoxy is so tempting to be used is the relatively easy production. Obviously you can store these two stable liquids, combine them when needed, which allows large-scale mass production. You can use moulds to create almost any geometries of samples, and as well as final products. And also the state of cure and the choice of which epoxy you use with which hardening agent to give you the materials that you desire, or sorry, the material properties that you desire. Obviously, for high voltage insulation, the best properties we're after are insulating and perhaps thermal conductivity, something like this. And also, one of the key points for this is that the solution phase that you go through while mixing the liquids is very tailored for addition of your micro and nano fillers. It's a lot easier to get these into solutions than extruding into molten polymers. Okay, so there's quite a lot you have to consider when you're making epoxy composites, some of which have already been covered, but just listing them on here. The curing time, the curing temperature for your resin and hardener combination, as well as the ratio between the two, as well as if you use moulds to create your samples. So just think of a jelly or a jello mould, just pouring your resin in and curing it with a hardener. It's often difficult to release it from the mould, so you have to consider any release agents you use or release films and the effect that this might have on your material. And then obviously your composite variables will be the filler you choose, the filler loading, the filler size, the compatibility with the epoxy, when you add it into your system, how well it holds its suspension, all of these different variables. So there's a lot to consider when we're making these materials. So the aims and sample production for this investigation. The aim was to simply establish a method at our lab for producing such epoxy composites, define the curing conditions and the suitability of the epoxy that we started the investigation with, have a look at any release agents, the sample quality that we were producing, and then add and disperse just a standard commonly used filler as a first stepping stone on the way towards producing better insulating materials. And then one of the key factors at the minute is that microfillers have obviously been used for many years now, and people are moving more towards nano because of the larger interfacial regions and the interfacial areas, which obviously defines the amount that the filler interacts with the matrix. So what we've taken is a standard DER 332 resin. We've used an amine Jeffamine D230 hardener. We've calculated the chemical ratio, which here is 1000 to 344. And we've taken a standard curing of 4 hours at 100 degrees. The filler we've chosen is a basic silica. We've chosen this mostly because it's been used quite a lot before in literature. They're spheres, so you don't get any of the gel rod-like effects with something like a Bowman system. We've taken 2 different sizes, so 1 to 5 microns and 5 to 15 nanometers. So a micro and a nano system. We've then created samples by adding the filler as a percentage weight to the total amount of epoxy, from 0 up to 10% weight. We've then tested these using DSC, AC breakdown for insulation properties, and dielectric spectroscopy for permittivity data. Just a quick mention of the sample production. Obviously, when I first came to this project, I hadn't worked with epoxies before. Instead, I'd been working with a polyethylene oxide system. So the first thing I looked at was simply stepping back and having a look at how to produce these samples. In general, for polymers, I feel that there's 4 main thin film production methods: spraying, pressing, coating, and casting. Obviously, I basically confirmed that using moulds and casting these samples is the easiest method. So you can see in the 2 figures, this is the mould that we produced and used. We actually found that the resin we used was quite difficult to get out of the mould without damaging the mould or the sample. So we've been using a QZ13 release agent, which works well for the system. Okay, so just a quick mention of how we make samples. We weighed out the resin and the hardener separately, degassed them to make sure that there aren't any air pockets inside. We then added the filler to the resin because it's more viscous. It will hold in suspension once we disperse it. We then mixed it all together, just using a very basic magnetic stir. The main aim for this is simply to see how easy it is to disperse these in a system. We're not aiming for perfect dispersion. We haven't used sonication or anything advanced like that at this stage. We just want to see in an industrial scene how easy it would be to produce these on a large scale. We then obviously degassed the mixture because the mixing will introduce air pockets. Introduced that to a mould and cured it to produce a thin film sample. So, having a look at the thermal results, we used a DSC. I'm sure most of you know about that, so I won't bore you with the details. Just having a quick look at the unfilled epoxy systems, one of the best ways to check on the curing state of the material is to look at your TG values. So as you can see here in the left figure, we've looked at the curing time for our sample with the TG on the y-axis and the curing time increasing on the x-axis. Just to establish that obviously the first initial points, the material hasn't fully cured, it's still fairly soft, we've got a low TG, and then at about 4 hours we see that it tails off and starts to level. So we now know that the material is fairly well cured, it's fairly stable. So this is a minimum curing time for us. In the same fashion, on the right hand side, we have the TG on the y-axis and the hardener ratio on the x-axis. Again, increasing up to a point and tailing off, showing that a ratio of 1000 to 344 is the lowest or the minimum that we should consider for this system. Again, doing the same with the curing temperature, has shown that 100 degrees is the minimum to make sure that we have a solid state of cure, which has given us these conditions for epoxy. Okay, so just having a look at the filled systems, the left-hand figure shows the micro-silicon dioxide filled system. And we can see that increasing the filler loading has caused a very slight decrease in the TG. Nothing major, but still within error and noticeable. This is mostly just due to an increase in free volume. Nothing really new to report there. However, on the right figure, when we add the nano-filled system, as we increase the filler loading, we see a large increase in the TG. Now, this is likely due to the larger interfacial area, as mentioned in the previous talk, When you have such a nano system, the interaction between the matrix and the fill are going to be a lot more significant. And obviously, in this case, it inhibits the molecular mobility within the system. Okay, so moving on to the electrical results. We used a custom AC breakdown kit, which is shown here. It just follows the ASTM standard, so I won't hold on that too much. Now this is just a quick slide to show almost a sidestep from what we were doing. If anyone was in the talk yesterday, this is the graph I was talking about. You can see here, we'll jump straight to the right-hand figure. This just shows the thickness of your material just against the breakdown strength. So as you can see, as you increase your material, this is relative, so it's kV per mil as well. As you increase the thickness of your material, it becomes less effective as an insulator. Now obviously when you're producing samples and you're comparing the same thickness, this isn't a problem because you can still compare your samples. But when you begin to compare samples of different thicknesses, you have to take this into effect, especially at the high end here, where the gradient is very high. So if you have a sample that's 70 microns and you want to compare it to something that's 90, you have to take this relationship into consideration. Okay. The left-hand graph there just shows the same. This is alpha value, sorry, from a variable distribution. The variable distribution is shown on the left. And as you can see, the breakdown strength still decreases to the left as we increase the thickness. So this was just a basic study of our epoxy, just so that if we couldn't produce samples of the same thickness to test, we knew the relationship that would align them all. Okay, so having a look at our microsystem, we first established that our unfilled epoxy at this thickness had a breakdown strength of 144 kV per mil, which is about standard for some of the epoxy systems that we've seen before. Once we added a small amount of the micro silicon dioxide, the breakdown strength is slightly decreased. Nothing major, but still worth noting. However, when we then added higher amounts of this filler, we see a much larger decrease. So this is likely due to the particles acting to shorten the breakdown path, and it's jumping between them as it goes through the material. The beta values, however, still suggest that the uniformity of the samples are fairly good. We did see that the beta value did drop from the unfilled epoxy to the filled systems, but we considered this as acceptable, as obviously there's going to be some agglomeration in the system, and it's not going to be as perfect as a standard epoxy. So moving on to the nano systems, addition of the 2.5% by weight, we actually saw no change in the breakdown strength. The graphs are a bit clumped together, but you can still roughly see what's going on. Obviously, this is likely due to the fact that it's dispersed enough that the nanoparticles aren't really acting as jumping sites as the breakdown proceeds through the sample. So this suggests that we've actually managed to disperse the filler to an acceptable level to not compromise the insulation properties of the material. However, once we add 5%, in a similar way to the microsystems, we do see a decrease in the breakdown strength. Again, this is likely to be the agglomeration effect occurring because our dispersion method isn't the best. And the agglomeration is going to cause the materials to behave more like the microsystems, in that we'll have the breakdown jumping across the fillers when in the matrix. Having a quick look at the permittivity values, we did notice that these are all taken at 10 Hertz, by the way. We did notice that the permittivity of the unfilled system was approximately what we expected for an epoxy system. However, the permittivity for both of the filled systems, the micro and the nano, has actually shown quite a large increase. Now this wasn't expected because the silica has a permittivity around the same as the epoxy. So something's obviously not right here. We had a look at this. And we've decided that what's likely happened is that the filler has actually collected water on the surface. So on the surface of the micro and the nano spheres, we're collecting a layer of water. Now, having a look at the standard mixing laws, and trying to understand if this would be the case. We've come to a fairly sure conclusion that this water is what's causing a higher permittivity and also the breakdown strength to decrease. So as the breakdown occurs, the jumping between the particles is actually jumping to the water around the edge of the filler, which is causing this increase in permittivity. This also ties in with the fact that the permittivity increase for the nano system is actually higher, so we have more interfacial areas. There's a lot more surface area involved, which means there's going to be a lot more uptake of water holding onto the filler. So it all ties together. Okay, so a quick conclusion. We've defined a method for producing these epoxy composites. We've outlined any important factors and considerations that we've taken into account when producing these materials. This is obviously the beginning of a longer term project, so we just wanted to make sure that we'd establish the basics before we move on. We've obviously decided on some basic curing conditions. It would be very nice to vary these and see how it affects properties such as breakdown strength. Obviously, it was mentioned in the first talk, the brittleness of the material. This obviously can cause problems when you do your breakdowns, because it's going to fracture mechanically as well as breaking down electrically. And then we've produced samples with 0 to 10% of the micro and the nano fillers, just to give us an idea of how an easily created fill system would respond. So we haven't aimed to disperse the filler perfectly. The main aim is simply to see how easily we could get it in there and the effects that it would have. From this, we saw that the micro silicon dioxide caused a decrease in the TG, just a linear decrease, whereas when we added the nano filler, we actually saw a large increase, so a curve towards the higher end. This was due to the dependence of the matrix filler interactions, so it's just a molecular mobility effect. When we looked at the electrical breakdown strength, we saw a steady decrease with the micro filler, whereas with the nano we saw that we could add up to 2.5% by weight without having a negative effect on the insulation properties. However, once we got up to a 5%, the very basic mixing methods that we were using aren't sufficient to stop the agglomeration of the filler, so it's therefore behaving more like a microsystem and breaking down at a lower voltage. When we looked at the permittivity, this obviously gave us a good indication of what was happening and why the breakdown strength was decreasing, simply due to the water absorption on the surface of the particles, which then led to an increase in the permittivity, which related to the surface area of the filler present. There's a lot of further work that obviously can be done here. Looking at different dispersion techniques would be one, to see how easily we could get this 5% dispersed so that there's no negative effect, or whether that's even possible at all. Removal of water from the particle surface. Obviously you're going to have to bake your filler to try and get the water out. And also any kind of surface treatment modification. So silanes are very popular for attaching epoxy groups onto your filler so that it will be very compatible with your epoxy system. And then obviously looking at different fillers just to try and improve the key properties for insulation, such as obviously the resistance to breakdown, thermal conductivity, factors like this. Okay. I'd also just like to thank the Anastasia project for their funding, and I'd like to welcome any questions or comments.
So your conclusion is that adding the nanoparticles is actually reducing the breakdown stress?
Yes, it is in this case.
Okay. And, well, that's fine. That's, I guess we need to investigate further. But regarding the moisture, is there any way to confirm your theory? For example, if you were to preheat your samples for a few days, we've been doing that for the same reason, that to drive any moisture.
Yeah. Well, that's definitely one thing that we want to look at. We were thinking that we would probably just if we bake or just warm the filler, just to try and remove any of the water before we then put it into an epoxy. The epoxies do go through a drying process before we test them, just to make sure, because obviously one of the main problems with epoxy is water uptake. But you try and remove the water once the filler is in the epoxy.
Yeah.
Okay, well that's something we could consider as well.
Before the experiments, we do that preheat for about 3 or 4 days.
Okay.
At certain elevated temperatures.
Yeah.
Then it's very nice.
Okay. Well, the consideration with that is that we cure our epoxy at around 100 degrees, which for a large number of epoxies is quite low. Whereas the temperature we believe that we'll need to drive the water away from the filler is probably going to be at least 120, 150. So we would then, if we did that to the filled epoxy system, we'd then be giving it a post-cure. So we have to then do that for all of the samples. So it might be a lot easier for us if we bake the filler and then add it into the epoxy for the standard cure. Okay, thank you for your question.
In this the global research, where you show the breakdown strength, the function of thickness,
Yes.
what is the slope of that curve in the low block?
Did you want to know the slope here, or
Yeah.
just the slope in general?
In general, because
In general.
low low.
I can't remember the exact equation, but I mean this is sort of a standard known behaviour.
Sure.
Yeah.
But the dependence will change. So
Yeah,
it
yeah,
becomes the
absolutely.
same for the nano composites, or this is the data for
This is just actually for the unfilled.
field.
Yeah, we haven't.
Do you have a data for the fields?
I do, but I don't have it with me.
Okay.
That's not in this paper, but we have collected it. Absolutely.
Thank you.
Stefan Mester from VA Systems. Have you had an opportunity to examine your dispersion quality of the SEM, or is that?
Yeah, we have done that. I haven't put it in here because, as I mentioned, the main aim is not to fully disperse the system, but we have actually considered using a SEM in the same way as the first presentation, just to gauge the dispersion of the film. But to be honest, mostly for this initial investigation, we didn't deem it that important because the state of the dispersion, I mean, it would be good to confirm that the 5% nano is agglomerating, as we believe it is in this data that we've seen. But yeah, that's absolutely something we're looking at.
Any more questions?